So now we've learned about separable differential equations and linear differential equations. And here we have Newton's law of cooling, where T is the temperature of an object and T sub E is the temperature of the environment that it's in. And H is some constant that somehow governs the way heat is transferred between the object and its environment. And previously we had said Newton's law of cooling is a separable differential equation. And because it's separable, we can always solve it by separating variables and integrating. So what we did was this, with some integral symbols, I guess. So we rearranged it like this, basically just dividing by this part. Now, one upgrade we can make to Newton's law of cooling is to make the environment temperature vary in time. And I claim that now we can do that. So before, we just had that T here was our unknown function of T, right? Now I'm saying we can also make the environment temperature not be a constant. We can make it be, we can make it be a function of time. It no longer becomes separable if we do that. So you can see if I try to divide by this and separate and integrate, it doesn't make any sense because this environment temperature might now depend on time, and I have not successfully separated, right? So I'm not in a situation where I can just change variables and make the integration variable capital T. However, it is linear. So now that we've learned about linear differential equations and the method of integrating factors, we can handle this situation where the environment temperature varies in time. And chemostats were another kind of pretty general system that we could handle when the differential equation was separable. So let me remind you how that worked. We'd have a tank with some, or a lake or whatever, a reservoir of liquid, and it has some volume V, and there's a fluid flow rate in and a fluid flow rate out, and then there's some stuff like salt or some chemical or whatever. And the fluid coming in has some concentration C in, and the fluid exiting has some concentration C of T, because you assume that everything's perfectly mixed, and you maybe use C of T for the concentration of stuff inside the liquid. And then you write down a differential equation, which basically goes like this. The time rate of change of the total amount of the green stuff inside here, so that's C of T times V, equals the rate at which green stuff enters minus the rate at which green stuff leaves. So we had decided that this fluid flow rate times the concentration of the fluid coming in, of the green stuff and the fluid coming in, that would be the rate at which the green stuff enters. And then this was the rate at which the green stuff leaves. And, okay, so V is not time dependent as long as Q in equals Q out, right? So we have been making this assumption. Q in equals Q out. And that makes V just a constant. Right? If the same amount of fluid goes in as leaves during any given segment of time, then the amount of liquid in the tank remains constant. And we've also been definitely assuming that Q in and Q out are constants. And we've also been assuming that C in is a constant. So all these things I've circled in blue are assumptions we've been making, which were needed to ensure that this differential equation is separable. So I hope you can see now that it is separable. So if I write it using, kind of the prime notation, it's V C prime, where C is the unknown function of T. Q in C in, that's now a constant, minus Q out C. And so I've written it, let me divide both sides by V. So here I have a constant, here I have a constant times C. It's separable, right? In fact, it's already separated. I just need to divide both sides by this thing, which is a function of C alone and not explicitly a function of T. However, now that we have learned about the method of integrating factors and how to deal with linear differential equations, we should be able to make q in and q out not be constant anymore. And we should be able to make even c in not be constant. We should be able to make q in and q out be constant and non-equal, so we should be able to get rid of this assumption too. So I think the most fun change to make, and I think the only one that I'll probably make on your homework, is no longer assuming that the fluid flow rate in equals the fluid flow rate out. So then this becomes no longer valid because v is now possibly a function of t. So I'm still assuming that q in and q out are constant, although I don't need to. We could actually handle them not being constants. But for now, let me just cross off this assumption and now just assume that these are all constants, these things circled in blue, but that q in might not equal q out. Then v becomes a function of t, and this is no longer valid because down here this required, this assumed that v was a constant when we took this derivative here. When we took this derivative here. Now that v is not a constant, we have to use the product rule to take that derivative. And I think when we do that, we get something not separable, or at least not necessarily separable. So let's use the product rule. We get cv prime plus c prime v equals q in c in minus q out c. And if I want to write that as c prime equals something, then I would write c prime equals, well, let me leave the v here and then divide it over after. So c prime v equals, and then I'm just going to subtract that to the other side, q in c in minus q out c minus v prime c. So this is what I would get, and then if I divide that v prime over, or if I divide that v over, then I have over v here, over v, over v. Okay, is that separable? Well, it doesn't look like it. Pay attention to where the t dependence is. So, of course, c depends on t, but I'm interested in where the explicit t dependence is. It's here, 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 and maybe even here. So this is not separated, and it doesn't look like it's really separable in general. So this is a situation that we couldn't deal with before. However, it is linear. It is a linear differential equation. And remember, the way we write linear differential equations is like x prime plus some function of t x equals some function of t q, right? So let me write it in that form just to show you that this is a linear differential equation. So it should be c prime plus some function of t times c, so plus something times c, equals something. And I just want to fill in what are these somethings. So I think to get just c prime here, I just need to divide everything by v. So here I will divide by v, and I should get v prime over v for this term, is this term. And then here I get q in c in over v minus q out over v c. That's not quite in the form I want yet, because I need to add this to the, well, because I don't want c's showing up on the right hand side. I just want a function of t. So let me add that to the other side. So what I'm going to do now is add this term to the left hand side. Just like that. And you see now we have c prime plus some function of t. This contains t dependence now. Here, possibly here, here, equals, or times c equals, and then some function of t. This also contains t dependence. Now, how would you find that t dependence? Say you wanted to know what is v of t exactly. Like if you want to solve this differential equation, you need to know what is v of t, right? Well, that's actually pretty easy. Let me show you over here. So say you want to find out what is v of t. It's another conservation law, but instead of conservation of the amount of green stuff, be it salt or toxic chemical or whatever, instead of conservation of the amount of green stuff like we're doing here, it's going to be conservation of volume. So the volume of fluid should be conserved. So it'll be ddt of the total volume of fluid equals rate volume of fluid in minus rate volume of fluid out. Okay, well the total volume of fluid is v, right? It's this v of t. And the rate at which fluid is entering is q in, and the rate at which fluid is leaving is q out. So here maybe v has units of gallons, then dv dt would be maybe gallons per minute, and these would be fluid flow rate, so also something like gallons per minute, just as an example. And if I'm assuming q in and q out are non-constant in time, then this would be complicated, but for now I'm assuming q in and q out are constant. Then my differential equation is just the derivative of v equals a constant. So the solution is pretty simple. It's v of t equals q in minus q out times t plus c. And then I have to find out what that c is using initial conditions. So hopefully I'm told, what is the volume of fluid initially? And then that would help me determine what is c. So you might have to do a little mini differential equation just to figure out v of t, and then you go put it in to this other differential equation, then you get this linear, you can rewrite it so that it looks like the standard form for a linear differential equation. Then to solve this, you would use the method of integrating factors. Okay, so I'm just showing you some examples of things that we have the power to do now that we can solve linear differential equations, which we previously didn't have the power to do.